All right, ready to dive in. Today, it's all about recurrent neural networks,
Yeah.
RNNs for short. Those things that are making waves in natural language processing.
Yeah, it's kind of crazy, isn't it? Computers trying to understand us, like really understand our language.
It's mind-blowing.
Yeah.
And you've sent over some really fascinating research about how they actually work, the challenges they face, and of course, the amazing solutions researchers have come up with.
Yeah, we're going to go beyond the basics, really get into the why behind these RNNs, not just the what.
I love that. So before we get lost in the acronyms, let's start with something called a language model. I always thought of it as like a scoring system for how natural language sounds. I'm on the right track.
Yeah, that's a great way to think about it. It's all about fluency, right? Making sure the machine's output actually sounds like something where a human would say.
So not just spitting out words, but making sure they sound right, like in a translation or something.
Exactly. Like if you have a machine translating a sentence, a language model helps pick the version that sounds the most natural.
I see, like a superpowered grammar checker.
Exactly. And it's not just for translations either. You use it in speech recognition too, trying to figure out what words are being said from an audio signal.
Okay, so it's helping computers understand and generate human-like language. Makes sense. But how does an RNN actually do that? Like, what's going on under the hood?
Well, think about how we read a sentence, word by word. RNNs kind of work the same way, processing information step by step.
Ah, so it's not looking at the whole sentence at once.
Nope, it's taking it one word at a time. And here's the cool part. At each step, it takes into account not just the current word, but also what it's learned from the previous words.
So it's building upon its understanding as it goes.
Exactly. It's like it has this short-term memory. We call it the hidden state. That's where it stores information about what it's seen so far.
So it remembers what came before and uses that to understand the next word.
You got it. And
Yeah.
then it combines that information with the current word to produce an output.
An output? Like what? What kind of output are we talking about here?
Well, it depends on what you're training it to do. It could be predicting the next word in a sentence, or maybe figuring out the sentiment of a text, like whether it's positive or negative.
Ah, so it's a pretty versatile tool.
Oh, absolutely. And a key thing to remember is that it uses the same set of parameters, you can think of them as the settings of the network, for every word in the sequence.
So it's not like it's reinventing the wheel every time it sees a new word.
Exactly. It's applying the same logic consistently. Now, let's say we want to build one of these language model RNNs. First, we need to feed it a ton of text data, books, articles, you name it. But before we do that, we need to do some prepping.
Prepping, like getting the ingredients ready before you cook.
Perfect analogy. We call it pre-processing. First, we break down the text into sentences, and then each sentence into individual words. This is called tokenization. Then, we often remove words that don't appear very often, like super rare words.
I guess those rare words wouldn't be very helpful for learning the general patterns of language, right?
Exactly. And then we add special start and end tokens to each sentence, kind of like bookends, so the RNN can learn about the structure of a sentence.
Okay, so we've chopped up our text, getting rid of the weird words, and added some markers. What happens next?
Well, now we need to represent each word in a way the RNN can understand, and that's where one-hot vectors come in. It's like giving each word its own unique barcode.
A barcode made of numbers, right? So the computer can process it.
Right. And the size of these barcodes and all the calculations involved depend on the size of our vocabulary. The more words we have, the more complex everything becomes.
Makes sense. More words, more computations, more work for the computer.
Exactly. And that brings us to another crucial step, initialization. Before we start training, we need to set up the parameters of the network. It's like setting up a new phone, making sure all the settings are right before you start using it.
So there's a right way and a wrong way to set things up from the beginning.
Oh yeah, if you don't initialize these parameters properly, it can really mess up the learning process. We usually use small, random values within a certain range.
So you're giving the network a good starting point, basically.
Exactly. And once we have everything in place, the fun begins. This is where we move into forward propagation. The RNN starts processing the sentences and tries to predict the probability of each word coming next.
So it's like reading the sentence and trying to guess what word comes next, based on what it's seen so far.
That's a great way to put it. And of course, it won't always get it right. So that's where something called cross-entropy loss comes in. It's basically a way to measure how good the RNN's predictions are.
So it's like a penalty system for getting things wrong.
Exactly. And we want to minimize that penalty, right? So to do that, we use an optimization algorithm called stochastic gradient descent, or SGD. This algorithm helps the RNN learn from its mistakes.
So it's constantly refining its understanding, getting better and better at predicting the next word.
Precisely. And to calculate these adjustments, we use an algorithm called backpropagation through time, or BPTT. It's kind of like tracing back through all the calculations the RNN made.
Trying to figure out where it went wrong so it could do better next time.
Exactly. But there's a catch, and it's a big one, and it has a pretty dramatic name: the vanishing gradient problem.
Oh, that doesn't sound good. Vanishing gradients, what's that all about?
Well, it's like this: imagine a really long sentence, and the RNN needs to capture the relationship between words that are far apart.
Okay, I'm picturing it.
Now, during this backpropagation process, the error signals from those later words need to travel back through all those layers to reach the earlier words.
And something gets lost along the way.
Exactly. It's like playing a game of telephone. The message gets weaker and weaker as it travels down the line.
So by the time it reaches those earlier words, the message is practically gone.
That's the problem. The error signals become so small that the RNN struggles to learn those long-range dependencies. It's like it forgets what happened earlier in the sentence.
So what can we do about it? Is there a way to fix this vanishing gradient problem?
There are. We can try initializing the weights differently, like giving those messages a boost from the start,
Right.
or use different activation functions. But, the real breakthrough came with the introduction of LSTMs and GRUs.
LSTMs, GRUs, more acronyms. What are those?
LSTMs stand for long short-term memory networks, and GRUs are gated recurrent units. They're special types of RNNs specifically designed to deal with this vanishing gradient problem. They can learn those long-range dependencies much more effectively.
RNNs with a superpower.
That's one way to put it.
All right, LSTMs and GRUs. These RNNs that can remember, that's what we're tackling now. It's pretty amazing how they solved that whole vanishing gradient problem.
Yeah, they really revolutionize things.
But remind me again, how do they actually do it? How do they hold on to information for so long?
It's all about these things called gates. Think of them like gatekeepers, right? They control what information gets through, what gets remembered, and what gets forgotten.
Yeah.
It's like a really smart filing system for language, I guess you could say.
Okay, gates. Got it. But we're talking about two different types here, right? LSTMs and GRUs. What's the difference?
Right. There are two main flavors. Let's start with the OG, the LSTM. Long short-term memory. That's what it stands for.
And they've been around for a while, haven't they? Like since the 90s.
Yeah, late 90s, and they're still going strong. Shows you how powerful they are. The key to an LSTM is this thing called the cell state. Think of it like a conveyor belt running through the network, carrying information from one step to the next.
So it's like the long-term memory holding on to important stuff even as it processes new information.
You got it. Now, the really clever part is how they control what goes onto this conveyor belt, what gets taken off, and what just keeps moving along. That's where those gates come in.
Okay, so what do these gates actually do?
Well, there are three main ones in an LSTM. You've got the forget gate, the input gate, and the output gate.
3 gates. Sounds pretty secure. So walk me through it. What does each one do?
All right, let's start with the forget gate. As the name suggests, it's all about deciding what information to forget, what to toss off that conveyor belt.
So it's helping the LSTM declutter, get rid of stuff it doesn't need anymore.
Exactly. It looks at the current word and the hidden state from the previous step. And then it uses a special function to decide what to do with each piece of information in the cell state.
It's not just a yes or no decision, is it? It's more like a dimmer switch.
You got it. It outputs a value between 0 and 1 for each element in the cell state. 0 means completely forget this, and 1 means keep this, it's important.
Okay, makes sense. What about the input gate? What's its job?
So the input gate is all about adding new information to the cell state, like taking notes, adding to that long-term memory based on the current word.
So it's constantly evaluating new information, deciding what's worth remembering.
Exactly. And again, it uses the current word and the previous hidden state to figure out how much of this new information should be added. It comes up with a value between 0 and 1, and that gets applied to this candidate state.
Candidate state. Like a draft of potential new memories.
That's a good way to think about it. So the input gate is making sure only the most relevant stuff gets added to that long-term memory. And then we've got the output gate, the last one.
Right, the output gate. What's its role in all of this?
Well, it decides what information from the cell state is actually going to be outputted to the next time step. It's like deciding what to share, what's relevant for understanding the next word in the
So
sentence.
it's like the LSTM is thinking, okay, here's what I need to remember to make sense of what comes next.
Exactly. And it does this by, again, outputting a value between 0 and 1, which is then applied to the cell state. And that's the LSTM's hidden state for that time step.
Wow, those three gates, they're like a little team working together to manage the LSTM's memory. It's pretty ingenious.
It really is. And that's the secret sauce. That's how LSTMs solve the vanishing gradient problem. They're so good at remembering things over long distances, they can finally capture those long-range dependencies that stumped those simpler RNNs.
Right, so LSTMs are basically RNNs with supercharged memories. Got it.
Hmm.
Now, what about GRUs? How do they fit into all of this?
So GRUs, or gated recurrent units, they came along a bit later, around 2014. Think of them as a streamlined version of the LSTM.
A more compact model.
You could say that. They still solve the vanishing gradient problem, but they do it with a simpler architecture. Instead of 3 gates, they only have 2, the reset gate and the update gate.
Okay, so we've simplified things a bit. What do these 2 gates do?
Well, the reset gate is kind of similar to the forget gate in an LSTM. It decides what information from the previous hidden state should be thrown away.
Still playing the role of the bouncer, making sure only the important stuff gets through.
Exactly. Now, the update gate is where things get a bit different. It's doing double duty, controlling both how much of the previous hidden state to keep and how much of the new candidate state to add in.
So it's like blending the old memories with the new information.
Exactly. It's deciding how much weight to give to the past versus the present. And that's basically how a GRU works. It controls the flow of information using these 2 gates, learning those long-range dependencies while being a bit more efficient than an LSTM.
Okay, so GRUs are like the more efficient cousins of LSTMs. Still powerful, but a bit lighter.
That's a great way to put it. Now, the big question, of course, is which one is better, LSTM or GRU?
Yeah, it's like choosing between 2 amazing tools. How do you know which one to use?
Well, the truth is there's no easy answer. Both have their pros and cons. It really depends on what you're trying to do and the data you have.
It's all about choosing the right tool for the job.
Exactly. GRUs, because they're a bit simpler, they're usually faster to train, and you don't need as much data. LSTMs, they can be a bit more powerful, especially when you have lots of data. But, the best way to find out is to try both and see what works best.
Makes sense. Experimentation is key.
Hmm.
But, you mentioned earlier that we can use something called pre-trained word embeddings to give our RNNs a boost. What are those exactly?
Great question. So remember those one-hot vectors we talked about where each word is kind of isolated in its own dimension?
Yeah, like each word gets its own little box.
Right. Well, word embeddings are different. They try to capture the meaning of words by placing them in a continuous vector space. Words that have similar meanings end up closer together in this space.
So it's like mapping words onto a map where their location represents their meaning.
Exactly. And the great thing is that these embeddings are usually pre-trained on tons and tons of data using some pretty fancy algorithms. So when we use them in our RNNs, we're basically giving them a head start.
Like they've already learned a lot about how words relate to each other.
Precisely. And it can really make a big difference, especially when we don't have a ton of data to train our own models. It's like borrowing knowledge from the experts.
It's amazing how far we've come, isn't it? From those basic RNNs that could barely remember what they just read to these LSTMs and GRUs with their super efficient memory management systems.
I know, it's incredible. We've really come a long way in teaching machines to understand us.
But I can't help but wonder, what does all of this mean for us, for the future of human communication?
Yeah.
It feels like we're on the verge of something big.
I think
you're right. It really does feel like we're at a turning point. It's exciting and maybe a little bit scary too,
Yeah, it's definitely a time of huge potential, but also some big questions. I think one area where we're already seeing the impact is in automation. Those tasks that used to require humans, like writing reports, translating languages, they're being done by machines now.
Yeah, it's amazing. And it's happening so fast. When I think about chatbots now, they're getting so good. It's almost like talking to a real person sometimes.
I know, right? And it's not just chatbots. We've got these virtual assistants that are getting smarter all the time. And all these new AI tools for creating content. It's really changing how we work.
It makes you wonder about the future of work, though, right? A lot of people are worried about AI replacing jobs.
Yeah, there are some valid concerns there. But I think it's important to remember that technology has always disrupted things, Think about the Industrial Revolution. Sure, it led to some job losses, but it also created whole new industries, new opportunities.
So you're saying it's not all doom and gloom.
Exactly. I think the key is to adapt, to evolve along with the technology. Instead of seeing AI as a threat, We should be thinking about how we can work with it.
It's about collaboration, not competition.
Exactly. And, AI has the potential to free us up from all those boring, repetitive tasks. We can focus on the more creative stuff, the things that require real human ingenuity.
It's like having a superpowered assistant, right?
Hmm.
Taking care of all the busy work so we can focus on the big picture.
Exactly. And think about how RNNs are changing how we interact with information, too. Those personalized news feeds, the recommendations you get online.
Just like they know me better than I know myself sometimes.
Right. And that's all powered by RNNs, analyzing tons of data, figuring out patterns, so they can personalize our online experiences.
And it's not just about entertainment, right? Think about education, personalized learning, tailored to each student's needs.
Absolutely. RNNs could revolutionize education. They can help pinpoint where students are struggling, provide personalized feedback. They could even create these adaptive learning paths that adjust to each student's pace.
That would be amazing.
Sure.
But are there any downsides to this kind of personalized information filtering?
Well, one concern is that we end up in these filter bubbles, echo chambers, where we're only exposed to information that reinforces our existing beliefs.
Yeah, that's a good point. If you only hear from people who agree with you, you might start thinking your way is the only way.
Exactly. So it's important to be aware of that potential bias and make an effort to seek out diverse viewpoints.
It's about finding that balance between personalization and exposure to new ideas.
Precisely. And, one last thing I want to mention is that all of this, it's still just the beginning. We're only starting to explore what's possible with these technologies.
It's exciting, but also a little bit daunting, right?
It is. And I think it's really important that we approach it responsibly. Think about the ethical implications.
It's not just about building smarter machines, it's about building a better future.
Exactly. And I think it's a future full of possibilities, where humans and machines work together to solve problems, to unlock new levels of creativity and innovation.
That's an inspiring thought. This whole deep dive has really opened my eyes.
Ah,
It's amazing what we're learning to do with these RNNs.
it has been quite a journey.
And a huge thank you to you for sharing your expertise with us. For our listeners who want to learn more, we've included some links to the research papers we talked about in the show notes.
And as always, we'd love to hear your thoughts. You can find us on social media.
That's all for today's deep dive. Thanks for listening.